Now, a few statistical terms that we will be dealing with and which we would want to get acquainted with are the confidence interval. So, the confidence interval is the range of values within which the population mean is expected to occur with a certain probability. So, it is the probability of the population mean occurring within a range of values, and these range of values is what we call as the confidence interval. This will become clear in the example that I will take in a little while. So, please bear with me, and the limits of this interval is known as the confidence limits. So, if I draw a Gaussian profile, I can find a confidence interval, and the limits of this interval is what is known as the confidence limit. To exemplify, let us see, or let us say that there is 95% probability that the population mean for, say, calcium in our blood lies in the range of 2.4 plus minus 0.2 millimolar. Now, this is the confidence interval, and the confidence level here is 95%. Okay. So, when we talk in terms of the confidence limits, which is the extremities of the confidence interval, the confidence limit for this data set is shown here, which is 2.2 to 2.6 millimolar. In other words, it is expected that 95% of the human population will have their calcium levels within this particular range of 2.2 to 2.6 millimolar. Now, as we can see that the confidence interval depends intricately on the confidence level that we want to report our data with. So, the confidence interval is abbreviated as CI, and the confidence level, which is the probability of finding the mean, is put in terms of the confidence level CL. So, if we want to, for example, if what we said in the last slide was that for 95% population, the normal blood calcium level is 2.4 plus minus 0.2 millimolar. Now, for single readings, the confidence interval for mu for a single reading is given as the mean value of that reading and plus minus z and sigma. So, z is the z score or z statistics which we have introduced already, and this will be dependent upon the confidence level of our reporting. Now, if the measurement is done for n multiple readings, then the confidence interval can be reported as x bar, which is the mean value of these readings, plus minus z sigma by root n, where n denotes the number of readings being undertaken. Okay. Now, let us consider the previous example where we said that the 95% population will have the normal blood calcium level of 2.4 plus minus 0.2 millimolar. Now, using these equations, let us call these equation 3 and 4, how do we calculate what would be the confidence interval for 99% of the population? So, for that we will use equation 3. What we observe is that Ci is equal to x plus minus z sigma okay, x bar, and x bar here is 2.4, and z value and sigma value is what we need to plug in here. Now, z value for 99% of the population can be found here, and the z value for 99% population is 2.58. The confidence interval of the population mean depends intricately on the confidence level of our reporting. So, if we want to report with a higher confidence level, we would want to use a higher z value, and that would imply that the confidence interval increases. So, as CL increases, this implies the CI also increases. So, which is also written below, that for larger confidence level we will require a larger confidence interval for the mean. So, what we have seen is that the confidence interval for mu is equal to x plus minus z sigma, because as we know that the z can take both positive and negative values. So, this for our data set was 2.4 plus minus 0.2 millimolar, right. So, for 95% confidence level, the z score is 1.96. So, plugging in this value, what we get is 1.96 into sigma is equal to 0.2, this value here, the right hand side term. Now, when we do the maths here, what we get is that the sigma value turns out to be 0.2 by 1.96, which is equivalent approximately to 0.1 millimolar. So, 0.1 millimolar is the standard deviation value for this data set. Now, when we plug in this value, so this all result was at 95% confidence level. If we want to increase the confidence interval for mu to 99%, we will have this value as 2.4 plus minus 2.58, which is the z value for 99% confidence level, into 0.1, which is the standard deviation for this data which we just calculated here. Now, when we do that, we get the confidence interval for mu at 99% confidence level as being 2.4 plus minus 0.26 by rounding it off. So, what we already see is that the at 95% confidence level, the spread was 0.2 millimolar. At 99% confidence level, this confidence interval need to be increased or expanded to 0.6 millimolar values. Now, let us go back to our presentation. So, what we observe is that if we are doing our measurements n times, or if we are repeating our measurement n times, the confidence interval can be written as x bar plus minus z sigma by root n. So, this equation is very similar to equation number 3, which is shown here, except that it incorporates the root n term, which is coming from the n repeat measurements that we have performed. So, what this equation also tells us is that the confidence interval at the same confidence level can be halved if we take 4 times the readings. So, for example, if our readings were or if our confidence interval was 0.2 in the previous case based on say 100 readings, if we take 400 readings, this can be reduced to 0.1 millimolar by taking 400 readings. Okay. So, a question can be that if we want to reduce the confidence interval to 1/3 of the original value, how many readings do we require? And yes, the answer is that we will require 9 times the original readings to get a reduced confidence interval which has been reduced to 1/3 the original value. Now, it is very important to keep in mind that the Z statistics can be applied only when we have very good estimate of the population standard deviation sigma. And when do we have that? We have that when a really large number of observations are available to us. So, we have a very good estimate of how a population is behaving, or in other words, when the sample size is quite large. Usually that is not the case. So, this question baffled initial statisticians in terms of what do we do if we do not have a good estimate of sigma, or to rephrase it, what do we do when we are dealing with small sample sizes. Now, this question was very effectively answered by William Gose, who is shown here from a Wikipedia image, and he, along with 2 other stalwarts of statistics, Carl Pearson, he is the same person in whose name Pearson coefficient is given, and similarly Ronald A. Fisher, in whose name other statistical tables are available. So, these 3 people laid the foundations of early statistics, which saw very rapid inclusion both in academics as well as in industry. So, what William Gose did was he developed statistical methods to analyze small samples, and there is an interesting anecdote to be told here. William Gose, when he was working on his analysis of small samples, he was working for a beer company which is known as the Guinness. Yes, it is the same one which gives the Guinness Book of World Records to us. So, Guinness had put an embargo that the scientists working for it will not be able to publish their findings if they have word beer in it, if they have word Guinness in it, or if they have their own surname. So, what William Gose did was to sort of overcome this embargo, he published his results with a pseudonym student in a journal which is known as Biometrica. So, he analyzed the beer samples and then he came up with a statistical tool that allowed him to analyze small sample sets and make predictions on a larger population. So, what William Gose did was to come up with a different statistics which is known as the T statistics. So, T statistics is quite similar to the Z statistics. So, if I look at the confidence interval, the same can be expressed very similarly. Just to recollect, it was z plus x bar plus minus z sigma by root n when we were dealing with the z statistics. And when we are dealing with the t statistics, this equation only changes the top part to the z is changed to t and the sigma, so z is moved to t and the sigma is converted to s, and the equation essentially remains same. Now the t value can be inserted from a table which is widely available in a variety of textbooks, and it utilizes two terms, one which is known as the degrees of freedom, which again has been already introduced, and the other one is the significance level. We will understand this in a little while, but before that let us look at how a t table looks like and how we can insert values from the t table. So a t table would look something like this. It has degrees of freedom and it has significance level. Different significance levels are given here on top based on the fact that we are dealing with a two-tailed test. We will discuss that also in the next class, so bear with me for a little while. But what it gives us are based on the degrees of freedom. For example, let us say here we have degrees of freedom 1 to 28. What would be the t values at different significance level? Now significance level is denoted as alpha and is nothing but 100 minus the confidence level in percent. So when we say 5% significance level, we are implying 95% confidence level for a two-tailed test. So what we see here is that as our degrees of freedom increase, the t value at a particular confidence significance level also decrease considerably. Okay. And another thing to keep in mind is that at infinite degrees of freedom, our t value will merge into the z value. So the numbers written here in the last line are all the z values at a particular significance level, and the significance level I have already explained is usually 100 minus the confidence level. So the key takeaways from the statistical t table are that the t values are larger than the z values at the same confidence level or significance level, and as a result when we calculate the confidence interval using the t statistics, the confidence interval would be larger or more spread out compared to the same confidence interval calculated using the z statistics. And another important thing that we saw just a little while ago is that as the number of measurements increase to infinity, the t value merges with the z value, or t statistics merges with the z statistics. So in other terms, what this table tells us that our predictability about the population increases as the number of readings are increased, and a limiting case of t statistics at infinite readings is the z statistics. So coming back to the confidence level and significance level, it is again important to emphasize that confidence level is the probability of finding the population mean within a certain interval of the sample mean. So we can take a small sample from the whole population, the sample mean will be different from the population mean, but if we analyze it properly, we will be able to make predictions about the population mean based on what the sample mean is and at what confidence level do we want to make that prediction. Now, the interval within which the population mean is supposed to lie is known as the confidence interval. The significance level, which is denoted as alpha, is expressed as percentage, and it is the probability of the result being outside the confidence level. Now, in other words, the significance level tells us about how significant or statistically significant that measurement value is. And as has already been told, that the significance level alpha for a two-tailed test is 100 minus the confidence level in terms of percentage. So, in the next class, what we will do is we will utilize some of these concepts to start calculating the confidence interval of the mean, and slowly we will get introduced to what is known by the one-tailed and the two-tailed tests, and we will use these tests to test the hypothesis that we are projecting. So, all that will be covered in the next class, and thank you for being with us. Good day.